The concept of wormholes has fascinated scientists and science fiction fans alike for decades. A theoretical shortcut through space-time, a wormhole could connect two distant points in the universe, allowing for near-instantaneous travel across unimaginable distances. If they exist and can be harnessed, wormholes would revolutionize space exploration, making interstellar and even intergalactic travel possible. But are wormholes real, or are they just the product of mathematical equations and Hollywood imagination? Scientists are actively studying whether these cosmic passageways could exist, and more importantly, if they could ever be used as a means of transportation. Understanding the nature of wormholes requires diving into the realms of general relativity, quantum physics, and advanced theoretical science, where reality often seems stranger than fiction. Wormholes, also known as Einstein-Rosen bridges, were first theorized in 1935 by Albert Einstein and Nathan Rosen as a solution to Einstein's field equations in general relativity. The idea suggests that space-time could be folded in such a way that two distant points become directly connected, bypassing the vast distances that separate them. In simple terms, imagine folding a piece of paper so that 2 points on opposite ends touch each other. This is the basic concept of a wormhole, where instead of traveling across the surface, one could move instantly through the fold. However, the existence of wormholes remains entirely theoretical. No observational evidence has confirmed their presence in the universe, and their stability is highly questionable. According to Einstein's equations, a naturally occurring wormhole would collapse almost instantly due to the immense gravitational forces at play. Some theories suggest that exotic matter, a hypothetical form of matter with negative energy density, could be used to keep a wormhole open. Without it, any traveler attempting to pass through would be crushed before reaching the other side. Despite these challenges, wormholes continue to be one of the most intriguing possibilities in modern physics. Scientists explore their potential not just for interstellar travel, but also as a possible means of time travel. If a stable wormhole could be created and controlled, it might allow for journeys across the universe at speeds far beyond the limitations imposed by the speed of light. This raises profound questions about the nature of space, time, and the fundamental structure of the cosmos. The question of whether wormholes could ever be used for space travel depends on several major scientific challenges, each of which must be addressed before humanity could even dream of harnessing them for exploration. The first and most fundamental challenge is the existence of wormholes themselves. While general relativity predicts that such structures are possible under specific conditions, no direct observational evidence has ever been found to confirm their presence in the universe. Even if wormholes do exist, they may be microscopic, appearing and disappearing at the quantum scale, far too small to allow the passage of a spacecraft or even a single atom. The second challenge is stability. In their natural form, wormholes are expected to be highly unstable, collapsing before anything can pass through. Theoretical physicists, including Kip Thorne, have suggested that exotic matter with negative energy density could theoretically hold a wormhole open, preventing gravitational collapse. This exotic matter would need to exert a repulsive gravitational force, counteracting the immense pull of the wormhole's walls. However, exotic matter itself remains hypothetical. No known particles exhibit the necessary properties to generate negative energy in sufficient quantities to stabilize a traversable wormhole. Some quantum field theories suggest that negative energy can exist in tiny amounts through the Casimir effect, but scaling this up to a cosmic level remains an enormous challenge. Another major hurdle is the extreme forces present inside a wormhole. Even if a stable wormhole could be created, the immense tidal forces generated by the warping of space-time could rip apart any spacecraft attempting to travel through it. These forces would stretch and compress objects in ways that would be catastrophic to anything made of conventional matter. Some models suggest that certain types of hypothetical wormholes, such as traversable Lorentzian wormholes, might be stable enough for safe passage, but these remain speculative. Furthermore, there is the question of how wormholes could be created, controlled and navigated. If natural wormholes do exist, they would likely be scattered randomly throughout the cosmos, making it incredibly difficult to locate and align them with desired destinations. Theoretically, an advanced civilization might be able to artificially create or modify a wormhole, but this would require energy scales far beyond anything currently imaginable, possibly on the order of entire stars or even galaxies. Some theories suggest that manipulating dark energy or utilizing the energy from black holes could provide the necessary power, but such ideas are purely speculative at this stage. Even if all these challenges were somehow overcome, another profound question remains: what would happen to objects passing through a wormhole? Some physicists propose that wormhole travel could be akin to entering a completely new universe, with different physical laws governing the other side. Others suggest that time dilation effects could result in strange paradoxes, where a traveler emerges on the other side at a different point in time relative to their departure. If wormholes do connect different points in space-time, they could, in theory, enable forms of time travel, raising deep philosophical and scientific questions about causality and the nature of reality itself. Despite the daunting scientific and technological barriers, wormholes remain one of the most fascinating ideas in theoretical physics. The prospect of instant travel across cosmic distances continues to fuel scientific curiosity, and researchers are actively exploring the potential of exotic matter, quantum gravity, and space-time engineering. If humanity ever finds a way to create and stabilize wormholes, it would mark the beginning of an entirely new era of space exploration, making the vast universe suddenly feel within reach. Until then, wormholes remain a tantalizing mystery, suspended between science and science fiction. Another critical challenge in using wormholes for space travel is the issue of causality and paradoxes. If a traversable wormhole allows instant travel between two distant points in space-time, it could theoretically be used for time travel as well. This leads to a range of paradoxes, such as the famous grandfather paradox, where an event in the past could be altered in a way that makes its own occurrence impossible. Some physicists argue that the laws of physics may include a kind of self-consistency principle that prevents such paradoxes from occurring, meaning that any actions taken through a wormhole would be constrained in such a way that history remains unaltered. Others propose that entering a wormhole could send travelers into a parallel universe rather than their own past, effectively sidestepping the paradox issue but raising more questions about the nature of reality. In addition to paradoxes, quantum effects play a major role in whether wormholes could ever be used for travel. Theoretical models suggest that quantum fluctuations might destabilize a wormhole the moment anything attempts to pass through. If exotic matter were being used to hold the throat of the wormhole open, quantum instabilities could cause the exotic matter to dissipate, leading to an immediate collapse. Some research suggests that quantum gravity, the yet unknown theory that unifies general relativity and quantum mechanics, might allow for stable wormholes under certain conditions. However, until a working theory of quantum gravity is developed, this remains speculative. Another issue is navigation. Even if a stable, traversable wormhole existed, entering it without precise control could be disastrous. Unlike traditional space travel, where a spacecraft follows a defined trajectory, entering a wormhole might be more like stepping through an unpredictable cosmic doorway, with no guarantee of where or when the traveler would emerge. If a civilization were to harness wormholes for transport, they would need to develop highly advanced methods for mapping and controlling them, perhaps by engineering artificial entry and exit points. Despite these challenges, scientists continue to explore wormholes as a serious theoretical possibility. Researchers in fields like quantum field theory and general relativity are working on ways to test for the possible existence of natural wormholes. Some proposals suggest that anomalies in gravitational lensing or unexplained cosmic radiation patterns could indicate the presence of a wormhole. If evidence of a naturally occurring wormhole were found, it would be one of the most groundbreaking discoveries in physics, providing new insights into the fundamental structure of the universe. For now, wormholes remain a speculative but fascinating possibility. If future advancements in physics allow us to understand and manipulate space-time on a deeper level, wormholes could move from the realm of theory into reality. Whether they turn out to be cosmic shortcuts, tools for intergalactic travel, or purely mathematical curiosities, their study continues to push the boundaries of human knowledge. If humanity were ever to harness wormholes for space travel, the implications would be profound. The ability to bypass vast cosmic distances in an instant could transform our understanding of interstellar and even intergalactic travel. No longer would space travel be bound by the slow constraints of rocket propulsion and relativistic speeds. Entirely new frontiers would open up, allowing civilizations to spread across the universe with unprecedented ease. This could lead to the formation of interstellar societies, where distant star systems are as accessible as neighboring continents on Earth. However, the potential risks of using wormholes for space travel are just as significant. If a civilization were to manipulate or artificially create a wormhole, even a small miscalculation could have catastrophic consequences. The collapse of a wormhole could release massive amounts of energy, possibly triggering destructive space-time distortions. If wormholes connect different regions of space-time, they might also link areas with vastly different physical laws, leading to unpredictable or even fatal outcomes for travelers. Additionally, if wormholes allowed travel across vast distances, they could also become a means of contact between different advanced civilizations. This raises complex ethical and security concerns. Would we be prepared for potential encounters with extraterrestrial life through a wormhole? Could an advanced alien species already be using wormholes, watching us from another part of the universe? The ability to traverse space in this way could make the universe feel much smaller and more interconnected. But it could also introduce existential threats that humanity has never faced before. From a philosophical perspective, the existence of traversable wormholes would challenge our fundamental understanding of space, time, and reality. If wormholes allow for time travel, could they alter the very fabric of history? Would civilizations use them responsibly, or could they lead to dangerous manipulations of the past and future? These questions highlight the need for caution in exploring such a powerful technology. Ultimately, wormholes remain one of the most exciting and enigmatic concepts in modern physics. While we currently lack the technology and understanding to create or use them, the mere possibility of their existence drives scientists to push the boundaries of what is possible. Whether or not we will ever travel through a wormhole remains uncertain, but their study continues to inspire new theories, experiments, and ideas that bring us closer to unraveling the deepest mysteries of the universe. If we were ever able to use wormholes for space travel, it would revolutionize not just our ability to explore the universe, but also our very understanding of reality itself. The implications would be staggering, far beyond what conventional space travel can offer. Instead of taking tens of thousands of years to reach even the nearest stars, we could travel across the galaxy and potentially even between galaxies almost instantaneously. This would mean that humanity's reach would no longer be limited to a single planet, solar system, or even one corner of the universe. It would open the possibility of settling on distant exoplanets, establishing interstellar colonies, and even creating civilizations that span across vast cosmic distances, all connected through these mysterious shortcuts in space-time. However, while this idea is tantalizing, there are enormous challenges to overcome before it could become a reality. The first is the stability of wormholes. Theoretical models suggest that naturally occurring wormholes, if they exist, would be highly unstable and would collapse almost instantly unless some unknown form of exotic matter, hypothetical material with negative energy, were used to keep them open. Without such stabilization, any attempt to enter a wormhole could lead to catastrophic results, with travelers being crushed as the tunnel collapses or spat out into an unpredictable region of space-time. Even if we found a way to keep wormholes open, controlling their destinations would be another massive challenge. Would they always lead to specific locations, or would they randomly connect different points in space-time, making navigation impossible? Another major issue is the energy required to create or manipulate a wormhole. According to Einstein's general theory of relativity, the warping of space-time on such a scale would demand energy levels far beyond anything currently imaginable. Some theories suggest that a civilization would need an advanced understanding of quantum gravity or access to vast amounts of dark energy to generate a stable wormhole. This is far beyond our current technological capabilities, but it does raise the possibility that other, more advanced civilizations, if they exist, may have already mastered this technology. Could wormholes be artificial constructs left behind by an ancient cosmic civilization? If so, would they be safe to use, or could they pose unknown dangers? Beyond the physical challenges, the potential for time travel through wormholes introduces even deeper complexities. If wormholes allow for travel between different points in time as well as space, it could create paradoxes that defy our understanding of causality. Would traveling through a wormhole allow someone to meet their past or future self? Could it lead to changes in history, altering the course of events in unpredictable ways? Some physicists suggest that nature may have built-in safeguards, such as self-consistency principles, that prevent paradoxes from occurring, but this remains speculative. If time travel is possible, the consequences would be profound, raising ethical and existential questions about how we might use such a capability. Furthermore, if wormholes became a means of travel, they could also become a pathway for encounters with extraterrestrial civilizations. If an advanced species has already discovered the secrets of wormhole travel, could they use them to visit us? Or could we unknowingly open a pathway to a region of space controlled by an alien intelligence? The risks of such contact could range from beneficial exchanges of knowledge to existential threats, depending on the nature of the civilizations involved. Even if no other intelligent beings are found, the sheer possibility of accessing different corners of the universe could forever change the way we perceive ourselves in the cosmos. At the heart of the wormhole mystery lies a profound philosophical question. What does it mean for space and time to be connected in this way? If wormholes exist and can be traversed, it would challenge the very fabric of how we understand distance, causality, and even the fundamental laws of physics. It would mean that the vastness of the universe is not an insurmountable barrier, but a navigable landscape, with secret passageways linking places that should otherwise be unreachable. Despite all these challenges and uncertainties, the study of wormholes remains one of the most exciting areas of theoretical physics. While we currently lack the technology and understanding to create or use them, the fact that they are permitted by Einstein's equations suggests that they could one day be within our grasp. Whether they remain a theoretical curiosity or become the key to interstellar travel depends on future breakthroughs in physics. If we ever manage to unlock their secrets, wormholes could transform humanity into a truly intergalactic species, taking our place among the stars in ways we can only dream of today. If wormholes could be used for space travel, they might provide a solution to one of the greatest obstacles in interstellar exploration, the vast distances between stars. Even at the speed of light, it would take over 4 years to reach the nearest star, Proxima Centauri, and thousands of years to explore even a small portion of our galaxy. Conventional space travel methods, such as chemical rockets or even advanced propulsion concepts like nuclear or ion drives, are limited by the immense time required to traverse such distances. Wormholes, however, would offer a way to bypass these limitations entirely by creating a bridge between two distant points in space-time. Instead of traveling across vast cosmic distances, a spacecraft could simply enter a wormhole and emerge instantly on the other side, no matter how far away. But while this concept is thrilling, there are numerous scientific and engineering challenges that must be addressed. One of the most significant is the problem of energy. Theoretically, wormholes require vast amounts of negative energy to remain open. Negative energy, which has been observed in small amounts in quantum experiments, could help stabilize a wormhole, preventing it from collapsing under its own gravitational pull. However, the amount needed to hold a traversable wormhole open long enough for a spacecraft to pass through is far beyond anything humanity currently has the ability to harness. Some theories suggest that exotic matter with negative energy density might be able to keep a wormhole stable, but whether such matter exists in a usable form remains unknown. Additionally, even if we could stabilize a wormhole, we would need to find a way to control where it leads. Would wormholes naturally form between two predetermined locations, or could we create and manipulate them to connect specific points in space-time? If a wormhole randomly links different regions of the universe, it could be useless or even dangerous if it opens in an inhospitable or unknown location. For instance, if a spacecraft were to enter a wormhole only to emerge near the event horizon of a black hole, the journey could end in disaster. Scientists would need to develop methods to predict and regulate where wormholes open and how they behave, ensuring safe passage through them. Another issue is the potential effects of traveling through a wormhole. Would entering one expose a spacecraft to intense gravitational forces or unknown quantum effects that could damage or destroy it? Some theories suggest that extreme tidal forces could rip apart any matter passing through an unstable wormhole. Even if stabilization methods are developed, the structure of space-time inside a wormhole could be unlike anything we currently understand, possibly creating unpredictable side effects. Could travelers experience time dilation, aging differently depending on where they emerge? Could wormhole travel lead to distortions in perception, memory, or even biological function? These are questions that physicists must answer before wormholes could ever be considered a viable means of space travel. Moreover, if wormholes connect different points in space-time, could they also allow for travel into the past or future? The idea of time travel through wormholes has fascinated scientists and science fiction writers alike. Theoretical physicist Kip Thorne and others have explored whether a traversable wormhole could function as a time machine, allowing someone to enter at one point in time and exit in another. If this were possible, it could lead to profound paradoxes, such as the well-known grandfather paradox, in which someone could potentially alter their own past. Some scientists believe that the laws of physics might prevent such paradoxes from occurring, but without experimental evidence, we cannot be certain. If humanity were to develop wormhole travel, it would have profound implications not just for exploration, but for the way we perceive our place in the universe. It could allow us to colonize distant exoplanets, establish communication networks across the galaxy, and even encounter alien civilizations. If other intelligent species have already mastered wormhole technology, could they have visited us in the past? Could UFO sightings or ancient myths about gods descending from the heavens be linked to advanced civilizations using wormholes? While this is purely speculative, the possibility of intergalactic travel through wormholes raises intriguing questions about the nature of intelligent life in the cosmos. Ultimately, while the concept of using wormholes for space travel is an exciting one, we are still in the very early stages of understanding their true nature. Current scientific models suggest that wormholes could exist, but whether they can be created, stabilized, and controlled for practical travel remains a mystery. If future advancements in physics, such as a deeper understanding of quantum gravity, provide us with the tools to manipulate space-time, wormhole travel could move from the realm of theory into reality. Until then, wormholes remain one of the most fascinating and mysterious possibilities in modern physics, offering a glimpse into a future where the stars are within our reach. One of the most intriguing aspects of wormhole travel is its potential impact on our understanding of space exploration and physics. If wormholes can truly connect distant regions of space, they could revolutionize interstellar travel, allowing civilizations to bypass the speed limit imposed by Einstein's theory of relativity. Current scientific research into quantum mechanics and general relativity suggests that space-time is not as rigid as once thought. Instead, it may be flexible enough to allow for shortcuts through the universe. Some physicists believe that if we can harness exotic matter or unknown forms of energy, we might be able to create and stabilize wormholes, effectively bending space to our will. However, the energy requirements remain a colossal hurdle. Theoretical calculations indicate that maintaining a traversable wormhole would require negative energy, a phenomenon that has been observed in small-scale quantum experiments, but never in quantities sufficient to manipulate spacetime on a large scale. If advanced civilizations exist elsewhere in the universe, they may have already solved this problem, raising the possibility that naturally occurring or artificially created wormholes could be used by extraterrestrials. Some scientists speculate that if aliens possess the knowledge to stabilize wormholes, they might be using them to explore or even visit different parts of the cosmos. Beyond the technological challenges, there are also major safety concerns. What would happen if a spacecraft entered a wormhole and encountered turbulence or instability inside? Could the gravitational forces within a wormhole tear apart anything that passes through it? Some theories suggest that unstable wormholes could collapse without warning, trapping or destroying travelers. To make wormhole travel practical, scientists would need to develop mechanisms to monitor and regulate their stability, ensuring that they remain open long enough for safe passage. Additionally, navigating through a wormhole could pose significant challenges. How would we determine the exit point before entering? Would there be a way to steer a wormhole to reach a desired destination? If wormholes allow for not just spatial travel, but also time travel, the implications become even more staggering. Some models suggest that traveling through a wormhole could result in arriving at a different point in time rather than just another location in space. This raises the possibility of paradoxes, such as events altering the past or future in unpredictable ways. Could a wormhole be used as a portal to observe historical events, or would the very act of traveling through it disrupt causality? These questions remain at the frontier of theoretical physics, pushing the boundaries of our understanding of time and space. Another concern is whether wormholes could be weaponized. If a civilization were to develop the ability to open and close wormholes at will, they might use them not only for exploration, but also for strategic advantage. A hostile force could theoretically create a wormhole to transport weapons, troops, or even entire fleets instantaneously across vast distances, making interstellar warfare a frightening possibility. If wormholes exist naturally, could advanced civilizations be guarding them to prevent misuse? Some have even speculated that certain unexplained cosmic phenomena, such as high energy bursts or anomalies in space-time, could be signs of wormhole activity, either by nature or by intelligent beings. Despite all these unknowns, The idea of wormhole travel continues to inspire scientific research and science fiction alike. Some of the most well-known stories, from Carl Sagan's to Christopher Nolan's, have explored the possibilities of using wormholes as gateways to new worlds. These depictions, while speculative, help fuel public interest in space exploration and theoretical physics, pushing humanity closer to unlocking the mysteries of the universe. In conclusion, wormholes represent one of the most fascinating possibilities in modern physics, offering a theoretical means of traveling unimaginable distances in an instant. While they remain purely hypothetical for now, ongoing research into quantum mechanics, exotic matter and space-time manipulation could one day turn them into a reality. If we ever develop the technology to harness wormholes, humanity may finally break free from the confines of our solar system and explore the vast universe like never before. Until then, wormholes remain a tantalizing mystery, one that challenges the limits of our imagination and the very fabric of our understanding of reality.